So good afternoon again. I'm Claudio Guarnaccia from University of Salerno, Department of Civil Engineering. I will give two presentations about acoustic emission technique for actually for non-destructive structural health monitoring. And the two presentations will be one on a specimen in prestressed reinforced concrete. The other one, it will be reinforced concrete. This work is pushed between the partnership between the lab of the strength lab, that is the structural engineering lab in our department, and we also have connected remotely Antonella Francavilla. I say hello to Antonella. And the leader of this group is Professor Gianvittorio Rizzano, that is also the head of the department. And the second lab is my lab, Applied Physics to Engineering Problems. So the idea when we started this collaboration, the idea was to apply acoustic techniques to make structural health monitoring. It's not innovation. We have plenty of literature on that, but we are pursuing this research in order to test this technique on a real site with special care to bridges, because there is a national project that is pushed by this ReLuis consortium. This is a consortium of structural engineering labs in Italy that is aimed at the development of guidelines for bridges. And within these guidelines, they are considering the possibility to include a section about acoustic emission for structural health monitoring and also for diagnosis, not only monitoring but also diagnosis. So as I mentioned, is it working? Okay. So the goals of these two presentations, you will see some slides will be repeated, but I will go fast on this. The goals are basically to assess the potential of this technique, to perform tests in the laboratory in order to be ready to go on site. And the results that I will show will be the analysis of the data that we collected for diagnosis. And this is an ongoing work, so this is the results that I will show are kind of preliminary, but they are very promising, so we really look forward to continuing this research. The framework in which we are moving is the structural health monitoring, and as you may imagine, this can be done in several ways, with the visual inspection, with the sensors that can be of several types, and very often regulations require to make destructive testing, like sampling of concrete or any other specimen to test in the lab in order to have an assessment of the health of the structure. But in the non-destructive domain, the idea is to be able to give the assessment of the health of the structure without compromising the functionality of the structure. And among the several non-destructive techniques, acoustic emission is a well-acquainted technique in the literature. How does it work, acoustic emission? The idea is that this acoustic wave, this mechanical wave, is originated at the source, that is the creation of the defect within the material. That can be concrete, can be steel, can be tuff or stone, any masonry, can be any kind of material. So the creation of the defect creates this mechanical wave after the release of energy, and this wave propagates in the material and can be detected by sensors that are put on the surface of the materials. Of course, there are several challenges in being able to detect this wave, because you have to deal with the frequency content of the signal. So you have to use the proper sensors. You have to have good coupling between the sensor and the material. You have to have a good readout electronics and so on. But we will see something about this in the lab test. Once you detect the signal, this can be processed and analyzed both in online or offline conditions in order to provide insights on the reason of the acoustic emission. The main parameters of an event, oh, sorry for the Italian, but this comes from a student presentation. We have the single event parameters that are mostly the threshold that is fixed according to the background noise. Then we have the duration of the signal and the amplitude of the signal, as well as the rising time. That is, we will see in one slide afterward, is very important to classify the crack, the event. And also we have the counts in terms of number of threshold exceedances. All these, and also the energy, that is the integral of the envelope. All these parameters can be used to calculate single event parameters of the acoustic emission or collective historical events, cumulative events, cumulative parameters that are used in literature to assess the health of the structure. So what is the idea? I will give example in this presentation mostly on bridges, because as I mentioned, this is the main aim of our research. So the idea is that we have a case study, we have a bridge that has some problems, and we want to analyze the problem, going back to the original design to check if there are any previous test results. Then we can have a visual inspection, and all these steps are preliminary to the choice that we will see in the next slides. And then we have to deal with the material, if it is concrete, steel, or mixed, or whatever. And the materials affect, of course, the propagation speed, and we have to deal with the original features of the materials compared to the real condition. As I mentioned, this is usually done with a specimen. Il carotaggio, I don't miss the word, but you go there, you take a specimen, and then you go in the lab and you test the compression strength. Sampling, yes, sampling. And but if you don't want to do this, you can go in the non-destructive techniques. And with the acoustic emission, what you do is you select the equipment in terms of sensors choice. And I will go fast on this, but there is a wide, let's say, range of possible sensors that can be used according to the frequencies. You can have resonant sensors, you can have wide range sensors. So according to the material and to the type of analysis that you want to do, you have to select the sensors. Also according to the background, so you can select preamplified or not preamplified sensors. If the background is low, you don't need preamplified. And then you select, you have to install these sensors, and the distance is influenced again by the material and the propagation speed. And there are some tests that I will show afterward to select the distance. And then you have to couple the sensor to the surface with a proper installation. Finally, you test the single sensor together with the entire set network of sensors, because the single sensor detects what we call the it of the acoustic emission, but the network is compulsory if you want to create an event that is localized in the space. So I go fast because I'm speaking already in 9 minutes. So I can skip this and go directly to the first laboratory test. So in this case, we deal with a prestressed reinforced concrete specimen, 2 meters, with these specifications, technical specifications. And the loading method that we selected was a 4-point bending test with a monotonic increasing load ramp. So we expect to have a region in the middle of the two forces that is with a constant bending momentum. And we will see this, how this will affect the localization of the events. The instrumentation that we applied, we chose a mixture of resonant sensor, the one on the top that has a first peak of resonance at 150 kilohertz, and also a wide range, a broadband sensor that is more useful for the low frequencies. But in the end, in the analysis, we will work only, since I will present only the localization analysis, we need to work with the same sensor, same typology of sensors. So we will present results only from the high frequency sensors. So we have the chassis with the readout electronics, the software, but I can go fast on this. If you are interested, we can speak afterward. First step is the threshold setting. So we had to check the background noise with the idling machine, already in touch with the specimen, in order to assess the background noise due to the vibration of the machine. Once we do that, we have to make the propagation test, and this is done. It is a very simple source that is used. Is a pencil break signal, and this is standardized in an international in the ISO standard. So the thickness of the pencil lead is fixed by the standard, and the idea is to produce these waves with the pencil lead break with increasing distance from the sensor, like as in this picture, and report the level of the signal detected by the sensor in this plot. And then we can calculate the propagation law and assess which is the maximum distance between two sensors in order to let the sensors speak each other, basically. So the idea in this case, we had a very long distance. This is not very common, at least with this kind of sensors. But in our case, our specimen was only 2 meters, so we didn't need to go up to 1 meter from distance from the sensors. So we selected this positioning of the sensors. The red one is the low frequency, but as I mentioned before, I will not present results from this, only from the 3 green high frequency sensors. And please note that the channel 1 is on the very left of the specimen, while channel 3 is in the middle and channel 4 is on the right side. This will be very important in the localization that I will show in a while. The loading curve is shown in the left plot as increasing, a monotonic increasing curve. The maximum load that the specimen was able to carry is reported in the slide. And on the right hand side of the slide, we have the panel that we see on the acquisition software. So you can customize this. It's maybe not very interesting, but you can select which kind of parameter you want to plot in terms of time, of channel, or peak amplitude, and so on. I will show mostly results on this one, the hits in terms of time, but you can see also this plot that is typical of the magnitude plots for earthquakes or other kind of applications. And here on the bottom right, you can start also seeing the localization, but I will go in details on this. So starting from the heat function, heat curve as a function of time, on the left side, you can see how channel 3, the red curve, basically increase a lot with respect to the other 2 channels. But this is quite expected result because, okay, I finished my first 15 minutes. So I need to hurry up. This is quite expected because that sensor channel number 3 was in the middle. So in the middle we have the higher momentum, bending momentum. So from the theory we expect to have the first cracks occurring in that area that are axial cracks due to the tensile stress of the material. And then you can see when approaching, we will see maybe better here, where in the right side we plot the energy as a function of time. And again, we see the red curve, the channel 3 that is making a separate story, let's say. But we can see around 65% a kind of step in the channel 1 and channel 4. And this is probably due to the starting of tensile stress, tensile events that occur after in a second stage of the loading test. And this is another plot to show not the cumulative energy, but the single event energy. So we can see where and when the most energetic events occurred during the test. And again, channel 3 is the the one that shows the most energetic events with almost one order of magnitude greater than the other channels. In fact, the right plot is just the same plot, but without channel 3, just to show you also the results about the lateral sensors. So they exhibit events, hits that are approximately one order of magnitude lower than the central one. And going to the localization, I think this is very, very interesting to see how basically what we do is to, it is like kinematic, very simple kinematic formulas of time of arrival to different sensors. So the software basically compare the time of arrivals of the events and assess the location, knowing the speed that is measured in the preliminary stage, the position of the event, of the source. So we can localize the events, and as expected in the first stage of the loading, most of the events are in the central part of the specimen. This is a peak amplitude as a function of the position in the x-axis. So this is a linear localization, not planar, not 3D. At the moment, only linear, because the specimen is very thick, not thick, narrow. So we didn't need 2D or 3D localization in this case. So we can see that the higher events in terms of amplitude occur in the central part. And the color of the dot is according to which channel detected first that event. And with the increasing of the load, we can see how more events come out in the lateral parts. And also in the last plot, we can see a cluster analysis that is pursued with the software provided by the Vallen system. This is an interesting insight, also compared, as you may see from the bottom pictures, with the occurring of the biggest cracks in the specimen that comes. It is indeed in the center part, but with a kind of a slight asymmetry on the right side of the specimen. And you can see how here we have this big crack occurring. And in the last slide of the results, I show how this localization perfectly fit the expectation, the theoretical expectation, the symmetry of the specimen and of the test. So, well, the conclusions can be done at the end of the next presentation. So I move here, and I present the second test that is done on a reinforced concrete beam, again in our lab, in the same from the same authors group. So I can skip this part and just draw you. I would like to highlight these results from literature. I put this. This is quite a recent work, 2022, from colleagues from. Okay, it's not very visible here, from Germany, because in Germany there is a working group that is doing basically the same, that has the same goal I mentioned at the beginning of issuing guidelines for bridges, especially in Prestressed concrete bridges in the case of Germany, and they are at the end of their study, and we got these results from this working group, but it's also published in this paper. And what they do was to measure a lot of acoustic emissions coming from real life bridges, and we have 3 bridges that are not functioning anymore, the colored dots, and 2 bridges with this grayscale that are operating. So basically, bridge A and bridge B are have been used for assessing the traffic noise in terms not the environmental noise, Roberto, that we are used to measure, but the acoustic emission in terms of ultrasounds produced by the traffic noise. And on these other 3 bridges, they basically produced the signals with artificial sources that are rebound hammer in the central plot, and they really cut the wires of the pre-stressing structure to detect the signal in order to have a benchmark to be able to issue a guideline. So the results that you see here are counts in terms of duration of the signal, and you can see that this result is not very promising, because the traffic noise that in our case is a background noise because does not give hint about damage in the structure, has the same pattern of the wire break. So this plot may say, okay, this technique does not work. But if we look at these other plots, we can see very different results. In fact, the amplitude as a function of the energy of the event is very different if we compare a breaking in the wire with respect to, let's say, to the traffic noise. We have higher amplitude, higher energy on average, and still also the rebound hammer has a different, this is used in order to have a benchmark when you go and put your sensors, basically the rebound hammer. And also if you look at the spectral centroid, you may see that the wire break is gathered in a range that is very below 30 kilohertz in terms of spectral centroid, while the spectral centroid of the traffic noise is higher. So this is very promising because it states that you can really indeed differentiate the signal coming from background noise, from traffic vibrations, with respect to a wire break. And this is the main idea that was implemented in a German bridge in Ulm municipality, in which they installed, these German colleagues installed a monitoring system with an alarm. It's like, the railway crossing. They have an alarm with the signal and barriers. If they detect a wire break, they close the bridge in real time, and they push alarm to the technician that is in charge of the visual inspection and the follow-up inspection. So we already have some real-life experience in the world, actually, in Europe but also in US. And so we really think that this is a promising technique that we want to pursue also in Italy. So going to the second test on a reinforced concrete beam, I will go fast on this because I'm running out of time. The idea is the same, a 4-point bending test. This time we had 3 channels positioned like in this plot, in this figure. And again, we have a monotonic increasing curve. The sensors are the same, and also the readout electronics. And you can see in this first plot how the 3 channels had different behaviors during the test. At the beginning, channel 1, that is on the left side, was not firing in terms of detection of hits, and also in the end of the test it will result as the lower channel in terms of lower ranking. It's like a podium, first, second, and third. So he ranked third. But the central channel and the right hand side channel, at the beginning they were firing together, but then we had an increase on the right side, but in the end the central the channel number two overcome definitely the other two channels. This kind of behavior is not very expected in some way, because we expected the central channel to be always higher than the other, as it was in the previous test. But as we commented with my colleagues in the strength lab, this is due to the fact that this specimen was let's say artisanal. It's not industrial. It was done in our lab, so probably it was not fully symmetric, and this was the reason why also if you look in this plot, the breaking was not very in the very middle of the specimen, but we had this asymmetry that is probably related to asymmetry in the design, in the building, not in design, but in the building of the specimen. And this was not true in the previous case, because that specimen was bought from an industrial company. So it was done with industrial processes. This is again the cumulative energy, and I can go fast on this, the localization, and you can see the red cracks that are, as I mentioned, the tensile cracks due to the bending, initial bending. Then we have this shear cracks, and in the last part of the test, we also see here in green the cracks coming from the compression in the top of the specimen after the bending. So also here we have the localization, and we can, I go back one slide just to show you how this technique was able already at 60% of the maximum load to predict the asymmetry of the asymmetric behavior of the specimen. So in some sense, this technique was able at 60% to predict where this structural element will fail. So it's a kind of, also for alarm purposes, seems to be feasible. So in the end, to conclude, the detection of the heats, I don't want to read, so just to underline that the heats, according to the channels, can give hint about the localization of the main sources in your structure. So can be used, for instance, in monitoring tests to follow up with a more detailed analysis related only to the section in which the maximum events have been localized. Also, the clustering in this test was able to highlight this asymmetry, and we can affirm that this results confirms that this technique can be used to as a structural, non-destructive structural health monitoring. What about future steps? Our idea is to start with on-field measurement campaign, and within the framework of the project that I mentioned, we have a bridge that has been assigned to our group. So the idea is to go on the bridge and to put the sensor and start some short-term, medium-term, and long-term data collection. We want to enlarge our measurement system that at the moment is with 8 sensors. And with this data, we can calculate also additional parameters, both of single event or cumulative. And last but not least, we are working on the classification of the cracks. I'm perfectly on time. Classification of the cracks. And this is a preliminary study. We will present this in Rhodos, dear Nikos. We are preparing the paper and we will submit for a Rhodos conference. And the idea is to separate cracks that are due to tensile stress from the cracks that are due to shear stress. And this can be done thanks to these two parameters, rise angle and average frequency. This is quite acquainted in literature. We want to test it on our specimen and on our hopefully real case study. Thank you for the attention.